Welcome to Lecture 5.3, Gram-Schmidt and Orthogonal Projection. We will continue to assume that X is an n-dimensional inner product space. In the last lecture, we showed why having an orthogonal, or even better, orthonormal basis is very convenient. In particular, it allows us to decompose an arbitrary vector into that basis, and the coefficients are just given by projections using the inner product. We'll start this lecture by showing how to construct an orthogonal basis given an arbitrary basis. This is called the Gram-Schmidt process, and it takes an arbitrary basis x1 up to xn and produces an orthonormal basis q1 up to qn that has the additional property that qk is in the span of the first k vectors of this basis. And that's noteworthy because it gives us an upper triangular matrix in what is called the QR factorization of A. So if we have a square matrix that's invertible, so the columns of this you can think of as x1 up to xn, it's a way to write that as a product of a matrix with orthonormal columns Q times an upper triangular matrix R. So more on that in a bit. Now let's see how this Gram-Schmidt process works. To begin, let's take x1, and q1's easy to just normalize that. So I'm going to actually add a short intermediate step, and you'll see why in a bit. So let's let y1 be equal to x1, and then I will let q1 be y1 normalized, so divided by its norm. So a picture of this is x1 is some vector like this, and if we normalize it, we get q1. And now x2 is going to be some vector out here. So I'm going to, first of all, well, let me sketch what I want to do. Now we don't know how many dimensions this lives in. You know, this could live in like 100 dimensions, and so this dotted line, I'm going to say this is like the hyperplane that's orthogonal to x1. So in two-dimensional space, it's just a line. In three-dimensional space, it's a plane, and so forth. So what we want to do is we want to project x2 onto this hyperplane, and then normalize that. So you can see that if we take x2 and we just project it onto here, then we get what I'm going to call this y2, and then I want to normalize y2. And if I do that, let me sketch the q's in red. So if I normalize that, then I'm going to get q2. So that's why I'm introducing this y1, because I'm going to have this intermediate step each time. Okay, so what is y2? So y2 is x2 where I subtract off the component of x2 into the x1 direction. So in other words, if I project x2 onto x1, this is the projection of x2 onto, I'm going to say q1, because q1 is the normal vector there. So let's write that down. So I'm going to let y2 be equal to x2 minus the projection of x2 onto q1. And then q2 is y2 normalized, and so forth. So let's do y3. So y3, it's going to be hard to draw this, but imagine that y3 is maybe, I don't know, in this direction, but it's sticking out of the board. So what we need to do is we need to project y3. We need to subtract off the components of y3. So y3 maybe is here coming right out of your face. Well, that's what we want it to be. So we got to subtract off the components that are in the x1 and the x2, the q1 and the q2 direction. So in other words, y3 is x3 minus the projection of x3 onto q1 minus the projection of x3 onto q2. Now remember the notation we've used. Capital P projection is for the actual unit vector. Not the unit vector. Capital P projection is the actual vector in this direction, where the previous lecture I used lowercase p projection for this length. So we do that, and we get that q3 is y3 divided by the norm of y3. So just a reminder, the formula for this projection, so this is q1. So this thing here is the inner product of x2 q1. So this is the magnitude of x2 in the q1 direction, and this is times the vector itself. So similarly, this thing here is x3 dot q1 times q1, and this is the inner product of x3 on q2 times q2. And then you can see how this goes. So in general, yk is xk minus the sum from I equals 1 up to k minus 1 times of the projection of onto qi of x, be careful here, xk. And then qk is yk normalized. And that's it. Now you can see by construction that each yk is automatically in the span of only the first. So I realized I put an x there. That should be an x. That should be an x. Oh, that's xk. I think I maybe just wrote an x instead of a k. So, so each yk is in the span of the first. Well, sorry. Each qk is by construction constructed only using x1 up to xk. So this thing holds automatically. And that's all there is to it. It's easy to check that this works. In matrix form, this leads to the so-called QR factorization or decomposition of an invertible matrix A, in this case defined by taking our input basis, x1 up to xn, and putting those as columns. And this says that we can write A as a product of a matrix Q times a matrix R. And Q has orthonormal columns, namely the output basis Q1 up to Qn, and the entries in R. So Rij is the inner product of Qi with Xj. I like to put the orthonormal matrix or vector in the second column, so I write that as Xj, comma Qi. And this is going to be an upper triangular matrix. And the reason why is because, well, this is actually true for all of the entries, but by this property right here, Qj being in the span of these things, that tells us right away that Qk, the inner product of Qk with X, L is going to be 0 if L is bigger than K. So these entries down here are still of this form, but they're going to be 0 by this property. Now let's see why this decomposition works. Remember, there's multiple ways to multiply matrices, and I think probably the easiest one is to think about multiplying Q times the individual columns. So if we do that, then x1 is Q times this column, and so indeed x1 is x1, inner product of x1 with q1 times q1. Then the second column is q times the second column here. And so that is going to be x2 is, so it's q1 times this first entry, so that's x2 dot q1 times q1 plus x2 dot q2 times q2, and so forth. And so I think you can see from this why this decomposition is going to hold. Now, we started here with a matrix A, and we constructed A from this basis, but you can see how this works in general. If I have any invertible n by n matrix, the columns are going to be a basis, and if I apply the Gram-Schmidt process, then I get a factorization like this. And the factorization also has other applications to, I think, linear least squares, to something called the QR algorithm, which is an algorithm involving eigenvalues, and there's other things as well. So I'm not going to go into those applications of it, but I just want to show you how the Gram-Schmidt process is encoded in matrix form. Thus far, we have talked about orthogonal and orthonormal bases and how to project onto individual vectors. So if this is like x1, we talked about how to take an x2 and how to project on this orthogonally. And this length is going to be the projection of x2 onto x1, which is the inner product of x2 with x1 over x1 dot x1. Now, in the Gram-Schmidt process, we subtracted off this, and we got something that was orthogonal to it. So this was x2 minus the capital P projection of x2 onto, I'm going to call it q1, the normalized version. And then I said that this lied in the so-called orthogonal complement. And you knew what that was probably from your undergraduate days. If this is R2, that's just a single line. If this lives in R3, then that's a whole plane. And if this lives in Rn, this is an n-1 dimensional hyperplane. But I haven't actually defined that as a subspace. Now, I didn't need to define it to be able to speak of it, because basically all we needed was the fact that these things are orthogonal. So in the remainder of this lecture, we will do that. I will talk about what the orthogonal complement of a subspace, not just of a vector, but of a subspace actually is. Now, earlier in this class, we found it helpful to think about dual vectors, or linear scalar functions, as row vectors. Going forward, it will be helpful to canonically identify these linear scalar functions, or dual vectors, with actual vectors in X. For example, the dual vectors we thought of as n-tuples, a1 up to an, as row vectors. And the vectors we thought of as column vectors, a1 up to an. So when I say identify these things, I'm really defining a canonical bijection between X and its dual space, X prime. Now, we earlier talked about a bijection between X and the double dual, because if you take the transpose of a vector twice, you get back the vector itself. And for there was a really obvious bijection between the vector X and the evaluation map of X. That just plugs in X. But here, in this setting, remember that I talked about L of X. Think about that as a dot product, as x1, I didn't use those words, xn times c1 up to cn, just as multiplying a row vector times a column vector. And this is the dot product. This is asymmetric by linear form. And if we have a vector space with an inner product, we can then, that will define the identification between the so-called dual vectors and actual vectors. In other words, this isomorphism that I want to define depends on the inner product. Here is the proper generalization of my claim that we can think of dual vectors as row vectors in a general inner product space. So every linear function, scalar function, L, can be written as an inner product of the input vector X with some fixed Y. Okay, so to prove this, let's first pick an orthonormal basis. So let's call it E1 up to En be not necessarily the standard unit basis, but any orthonormal basis, and orthonormal basis for X. And now remember the big idea that once we have an orthonormal basis, any inner product basically behaves as the dot product with respect to that orthonormal basis. In other words, the norm of X, or let's let X be A1 E1 plus all the way up to AN XN. Remember the norm squared of X is A1 squared plus AN squared. In other words, this is inner product of X with itself. So how do we find Y? What Y is going to do the trick given this unknown linear function? Well, let's apply L to this basis. So I will let Y be B1 E1 plus Bn xn, where Bk is just L of Ek. And I claim that this works. Because, what is L of x? L of x, you can see L of this thing is just going to be A1 L of E1 plus AN L of En. And this is just A1 B1 plus AN Bn. And remember that the inner product of x and y, if we have an orthonormal basis, is just going to be A1 B1 plus all the way up to AN Bn. It behaves just like the dot product with respect to an orthonormal basis that's orthonormal with respect to that inner product. So that's all we had to do. It's as easy to check. As a corollary, for any fixed y, there's a canonical isomorphism that takes the vector y to the linear scalar function that I just described up above here. So I will write this function as just blank dot y. I think I did this before, so this is what we get by fixing y, and the blank refers to the variable that we are plugging in. And I'm going to call this r. Y, I don't know if this is a standard. My choice of r is because I'm putting y in the rightmost coordinate. I mean, you could also call it L y because the left coordinate is the thing that you are plugging into. So again, I don't think there's a standard for this. I'm calling this ry, but there is also an analogous isomorphism, call it Lx, that takes a vector x and plugs in something to the right-hand coordinate and sticks x in the left-hand coordinate. Now these are really almost the same map because, this inner product is symmetric by linear form. So this inner product is also going to be y comma blank, and this is going to be blank comma x. So this, again, this thing defines the same map. In the case that we have a real vector space, things will get different when we have a complex valued vector space. I've talked about that before. Because we lose the bilinearity condition, it gets turned into, it gets slightly generalized, involving the complex conjugate. So more on that later, but for now we have two isomorphisms that are basically the same isomorphisms, ways that identify a vector with a covector, which with respect to an orthonormal basis, we can think exactly as we did before. Think about these dual vectors as row vectors, and think about these vectors, regular vectors, as column vectors. Now, I can properly define the orthogonal complement of a subspace Y of X as the set of vectors, X or little x, that are orthogonal to everything in Y. Now recall, in the beginning of this class, I defined something called the annihilator of y. And I used the same notation. That was the space of all, or the set of all linear scalar functions, or dual vectors, such that L of y equals 0 for all y in big Y. So equivalently, the set of all L in the dual such that L of y equals 0. So this is written in scalar product notation. And it should be clear that under the identification of x with its dual, in other words, given association of y with blank comma y, or actually maybe I should say x with x comma, these are the same map. In other words, declaring row vectors and column vectors to basically be the same. In other words, associating a1 up to an with a1 up to an, that these two definitions, or these two sets, agree. They coincide, which is why I use that same notation. Now I will prove something that's probably obvious to you. That's for any subspace Y, X is the direct sum of Y and its orthogonal complement. So how do we do this? We need to take an arbitrary element in X and show that we can write it uniquely as something in Y and something in its complement. So let's write that down. So let's take any vector x, and our goal is to write x as y plus y perp, where y is in big Y and y perp is in big Y perp, and the key is uniquely. So let's start with uniqueness. Let's suppose that we can write it like this, two different ways, that they have to be the same. So uniqueness. So let's say that I write x as y plus y perp, but also as z plus z perp, where y and z are in Y and y perp, z perp are in the orthogonal complement. Now I'm going to subtract these two things. If I subtract them, then let's see what we get. So we get y plus y perp minus, or z plus z perp equals 0. Or said differently, y minus z equals z perp minus y perp. Now y minus z is clearly in Y, and z perp minus y perp is in y perp, because these are both subspaces. So this is in Y intersect y perp. I claim that these two subspaces intersect trivially. And let's see what, in other words, that this has to be 0 and that has to be 0. If we can show that this is 0, then we have uniqueness automatically, because then these two sums are equal. So let's show that. So why is this equal to 0? Well, to show a vector is equal to 0, one way to do it is to show that its norm is 0. So what's the norm of y minus z, or what's the norm squared of y minus z? Well, that's the inner product of y minus z with y minus z. And we know that this first term is in Y. And we also know, because it's in the intersection, that it's in Y perp. So by definition, things in Y perp are things whose inner product with things in Y are 0. So this has to be 0, because this is orthogonal to that, and that's how we show that this is 0. And so that confirms uniqueness. So now let's do existence. So what I will do is start with an orthonormal basis of y. And we know we can do that by the Gram-Schmidt process. So let's let, say, y1 up to yk be be an orthonormal basis of y. Now we can extend this to a basis, say y1 up to yk, yk plus 1 up to yn of x. Now we cannot guarantee that this yk plus 1 up to yn is necessarily going to even lie in y perp. So as in sort of a guiding example, let's suppose we have x1 here in R3, x2 here, and suppose x3 sort of is off in that diagonal direction. And so the orthogonal complement of the xy plane y is the z-axis, and x3 doesn't lie in there. But what we can do is we can take these remaining vectors and we can apply the Gram-Schmidt process. So given these first k vectors, we have a partially completed Gram-Schmidt process. These are orthonormal, so we can keep going. So let's write that down. So by the Gram-Schmidt, we can get an orthonormal basis y1 up to yk. And then let's write this as zk plus 1 up to zn. Now I claim that zk plus 1 up to zn, all of these guys are in y perp. And that's easy to see. Let me write that up here. So note, if I take or the inner product of y with zi is 0 for all y in y, and that's easy to see why, right? Because y can be written using y1 up to yk, and those are orthogonal to each zk. So indeed, these things, each of these, or not these, each of the zi's, so each of the zi's is in y perp, and because this is a basis, this is our construction, this is our existence of given any vector in x, we can write it as a sum of things, or as a sum of a vector in y, that's the linear combination of these guys, plus something in y perp, that's the linear combination of these guys. Let me finish with one more comment. So in the beginning of the class, we talked about the direct sum of subspaces. So they had to intersect trivially, and they had to, and their sum, the regular sum, had to be the entire space. So in this picture, the span of x3, or xr3 is the direct sum of the xy plane and the span of x3. So these are complement subspaces, but they're not orthogonal complements. So for orthogonal complements, you also need this orthogonality condition right here. One more thing. Earlier in the class, when we talked about the annihilator, we couldn't prove something like this because in the beginning of the class, the annihilator lived in, or it was a subspace of the dual space. But we could prove something analogous to this. We proved that the dimension of y plus the dimension of y perp added up to the dimension of x. And that's still true right here. Let's now pause for some familiar examples. The first one, Rn with the standard dot product. I don't think I need to say much about this, but let me just remind you that if I take y to be the x or y axis, either one of these, let me take y to be the x axis, then y perp is the y axis. Now, why am I doing that? It's because I really want to compare it to an example that we did in the previous lecture of R2 with a curious inner product involving this symmetric matrix 2, 1, 1, 2. So if you recall here, I defined E1 to be 1, 0, E2 to be 0, 1, which we normally think about as being on the x and the y axis, and these things being 90 degrees. However, the cosine between these two vectors in this strange geometry is E1 dot E2 divided by the norm of E1 times the norm of E2. And remember that these things actually had norm root 2. And so this was actually 1/2. So the angle between these things is like 60 degrees. So you can think of this as 1, 0, and you can think of 0, 1 as lying up here. So, in other words, you can either think of these as not lying on the axis that we normally view them as, and having a 60-degree angle, or you can actually put them on the axes that they normally belong on and think of this angle as actually 60 degrees. So somehow your intuition is going to be a little bit non-Euclidean or different. But what I want to ask here is, if these meet at a 60-degree angle, then what is orthogonal to 1, 0? Because it sure ain't that one. So I want to ask you, what vector is this v? So let's do that now. So let's see what is orthogonal to E1. So E1 dot v is, using this definition, that's going to be, let's say that v or b is v1 is b1 b2 b and v, sorry. So that's going to be b1 b2 times 2 1 1 2 times 1 0. So let's multiply this out. What do we get? We get b1 b2, and then this is 2 1, and this is 2b1 plus b2 equals 0. In other words, whatever the heck b1 is, b2 is negative 2b1. So if b1 is 1, then b2 is negative 2. So if we think about this in the regular xy plane up here, this is that line with slope negative 2. So b is equal to 1, negative 2. So these two lines, so in this strange geometry, these two lines, this and the x-axis, are orthogonal. Or if you embed them here, the vertical vector is 1, negative 2, and this is 1, 0. Of course, this is not an orthonormal basis. If I wanted to do that, I could take v divided by norm v. Let's quickly see what that is. Norm v squared is v dot v. So that is 1, negative 2, 2, 1, 1, 2, 1, negative 2. So this is 1, negative 2. And now we get 2 minus, so this is 0. And then this is 1 plus negative 3, right? So this is 6. So so the norm of v is root 6. So this is going to be 1 over root 6 and negative 2 over root 6. So now if we take this vector and 1, 0, this is an orthonormal basis. So I like this example because it abstracts the notion of inner product, and it gives a little unusual definition for what we mean by perpendicular or orthogonal. Our third example is the space of linear maps from x to y. And the inner product, we've done this example before, is the trace of B transpose A, where if you wrap your head around it, ends up being basically like the standard dot product. So let me explain what I know I did this in a previous lecture, but if this is A and this is B, we take the inner product of these. This is A11, A12, A21, etc. B11, B12, B21, etc. Then what we end up getting is just like multiplying corresponding entries and adding them up. So A11, B11 plus A12, B12, etc. So it's really like if you were to dissect these, chop up the columns and stack them to get one large vector, and then just take the standard dot product. So for my example here, what I actually want to talk about is the example where x and y are the same. So I'm going to actually turn this, turn this y into an x, because now, oh, you know what? I just realized I should not have reused x here. So let me call this guy a v instead of an x. I'm having trouble with namings in this example, but now our matrices are square, and I'm going to let y be the subspace of symmetric matrices. So if we think about what that looks like, A11 can be anything. A12 can be anything. A22 can be anything. A13 can be anything. But these things strictly above the diagonal force the things below the diagonal. So the 2-1 entry has to be A12. So these have to be the same. The 3-1 entry has to be A13. So these have to be the same, and so forth. So what we get is we have free choice for everything up here, and then everything below that is forced. So the dimension of y is 1 plus 2 plus 3 plus all the way up to n, which is n times n plus 1 over 2. Now I claim that y perp is the space of skew symmetric matrices. We talked about skew symmetric linear forms. I feel like skew symmetric matrices probably came up in that lecture whenever it was a while ago. But what that is that means that Aij has to be negative Aji. So that's going to force all of these terms on the diagonal to be 0, because Aii equals negative Aii. And now if we have A12, this has to be negative A12. This is A21. Sorry, A13. This has to be negative A13. So in other words, these have to be the same. These have to be the same, etc. And now it's easy to see, what entries are free. You can pick anything you want above the main diagonal, or equivalently below the main diagonal. Let me highlight that just as a complement for up here, and it's easy to see for this what the dimension is. So the dimension of y perp is just however many entries are below the main diagonal. I think it's easier to write that as n squared minus n times n plus 1 over 2. Clearly, every matrix can be written as a sum of a symmetric and a skew symmetric matrix. Actually, maybe that's not clear, but hopefully it's clear that these are complementary subspaces. That every matrix can be written as a symmetric and a skew symmetric, and then uniqueness follows from the dimension argument. So I'm not going to go into the details here, but I want to show you that this is a standard thing to do, is to break up this space into a symmetric and a skew symmetric subspace, and these are orthogonal with respect to the standard inner product. Our last example is going to involve the 2π periodic functions with the inner product given by this integral. And we don't need this scalar out front, but remember that makes the sine and cosine waves orthonormal instead of just orthogonal. So I'm going to let y be the space of even functions. And that means that a function is even if f of negative x equals f of x. So in your head, you should think about that an even function is like a polynomial of even degree, or is like a cosine wave, something like this. And in fact, if you write an even function as a Taylor series that's going to have only even powered terms. I claim that y perp is the space of odd functions. And an odd function satisfies f of negative x equals negative f of x. So even just means that it's symmetric about the y-axis, not the same y. And odd means that it is symmetric about the origin. And by that I mean if you have a function like this, you need to reflect this piece across the y-axis and the x-axis. So if this is x and this is negative x, then these heights are opposite and equal. So examples of odd functions are, any x cubed. Sine waves are odd, and no surprise here. What's going on is any function whose, if you write it as a Taylor series, has only odd powers is going to be odd. So I claim that these are complementary. In other words, that every function can be written uniquely as something as an even plus an odd function. How do you prove that in general? Well, one way is to just do that. If you take I claim if you take f of x, and I can write it as f of x plus f of negative x over 2 plus f of x minus f of negative x over 2. This, by construction, is even. If you switch the roles of x and negative x, you get back itself. This, by construction, is odd. If you reverse the roles of x and negative x, the sign flips. And it's not hard to see that this decomposition is unique. I'll let you verify that if you want, but that shows that these things are indeed orthogonal complements. And notice that this does not require anything about, I said periodic. This does not require the function to be continuous or differentiable or anything like that, or even piecewise. This holds more generally. You've also seen things like this before. You've seen e to the ix is cosine of x plus I sine of x. Slightly different because we're over the complex numbers here, but this is the even part and this is the odd part. Perhaps you've also seen e to the x written as cosh of x plus sinh of x, hyperbolic sine and cosine, and indeed the formulas for cosh and sinh are e to the x plus e to the minus x over 2, and e to the x plus e to the minus e to the minus x over 2. Okay, so that's where orthogonal complements come up, even in an infinite dimensional space. It's an important concept. Our last concept in this lecture is that of an orthogonal projection onto a subspace, not necessarily a vector. We have talked about what it is to take x1 and project x2 onto that, but now Y is a generic subspace, and it has an orthogonal complement, and we'll define the map Py to be the orthogonal projection of x onto y, and we'll define that by taking an arbitrary vector x, writing it as a sum of, uniquely, as something in y and something in y perp, so y plus y perp, and then just truncating the y perp. That's the orthogonal projection. It's easy to show that this map is linear, and it's idempotent, which means that if you apply the map twice, it's the same thing as applying it once. And think about geometrically what a projection is. If you have a subspace you're projecting onto, if you do that once, you do it again, you don't get anything more the second time. So algebraically, this relation means that it satisfies the polynomial t squared minus t equals 0. That means that the minimal polynomial divides t squared minus t, which is t times t minus 1. In other words, the minimal polynomial is either t minus 1, or t times t minus 1. Of course, this first case is equivalent to, or only happens if the map is 0 itself. So y is the 0 vector. So we are projecting onto the 0 vector. This is the minimal polynomial if and only if the projection map is the identity, which means that that is a projection. That's an orthogonal projection onto the entire space. So for all other subspaces, not the trivial one, not the whole space, the minimal polynomial is going to be t times t minus 1. So this is otherwise. And because there are no repeated roots in the minimal polynomial, it is diagonalizable. So it's got a full set of eigenvectors. And the eigenvalues are precisely 0 and 1, and both of them do arise. So let me just write that down. The eigenvalues are lambda 1 equals 1, lambda 2 equals 0, without loss of generality, it doesn't matter how we label it, and then all other lambda k's are 0 or 1. We will now finish with a characterization of the orthogonal projection map in terms of the norm. This is something that I claim is very obvious in Euclidean space, but not so much necessarily in a general inner product space. So it's something that it's believable, but something we still have to verify. So this says that the projection of x onto space y is just the argmin. So this means the argument of this set, in other words, the vector in y that minimizes the norm of x minus y. So what is this saying? Let me draw a picture. Here's y. Here's x. It's a vector up here. And what I claim is that if we project x onto y, what we'll get is, let's call this vector y, that if we look at all other vectors, say z in big Y, then the norm of x minus z is at least as big as the norm of x minus y. It's going to be strictly as big, but we don't need to actually prove that. So, of course, x minus z is this vector in that direction, and x minus y is right here. So once again, this is obvious in Euclidean geometry, but not necessarily obvious in that geometry I gave you where involving the matrix 2, 1, 1, 2. Remember, this is the one where our standard basis vectors 1, 0 and 0, 1 met at a 60-degree angle. And yeah, I know maybe I should have rendered it a little differently, so they actually meet at a 60-degree angle and called this 1, 0 and 0, 1. But still, angles and lengths are a little bit weird here, so it's not clear that this necessarily is going to hold, but it does. So let's prove this. It's actually very straightforward. It's just from the Pythagorean theorem. So let's let x equal y plus y perp. So the projection, remember, is given by this definition. So p y of x equals p big Y of x is little y. So I'm going to take this x minus y, or sorry, this x minus z. So x minus z is y plus y perp minus z, which I'm going to rearrange a little bit. I'm going to write this as y minus z plus y perp. So y minus z is this distance, or this vector right here. And then by the Pythagorean theorem, which remember holds in a general inner product space, says that the norm of x minus z squared, norm of this, is the norm of that. Well, and I guess by the Pythagorean theorem, it's the norm. This is in y minus z. Y perp is in big Y perp. So we can write this as the norm of y minus z squared plus the norm of y perp squared. Now y is fixed by x. So is y perp. But what's variable, what's changing is z. So z can be anything in y. And so the question is, how do we minimize this right-hand side? We can't touch that, but z can change. And it's very clear that this is minimized when y is equal to z. Because in that case, this is 0. And that's the smallest this can ever be. And that's exactly what we needed to prove. When z is on top of y, when this distance is 0, that is precisely when this y perp, this, or I guess this difference of x and y is exactly y perp, and its norm is minimized. Okay, so that takes us to the end of the lecture. What we will do next time is talk about least squares. You probably know this from like your high school science class. It's the best fit line to data, but really what's going on behind the scenes is a projection, or an orthogonal projection, to some high-dimensional subspace. And a whole lot of statistics and linear regression, hence the name, is just the projection. So we'll talk about that application. We'll also talk about how to write the orthogonal projection in terms of a matrix. For that, we will need something called the adjoint, which is a lot like the transpose, but it is defined for an inner product space. So if we change, the transpose doesn't depend on the inner product, but for the adjoint, if we change the inner product, we get a different adjoint. So that's going to come up next. And this idea of projection is extremely important in so much of statistics and applied math. So stay with us. See you then.